Welcome. What you are about to watch is not science fiction, and it is not folklore. It is a serious investigation into one of history's most compelling unresolved questions: the mystery of the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it. Across the world, in universities, research institutes, and field excavations, serious scholars are wrestling with evidence that does not fit the accepted story. Evidence that has been documented, measured, and peer-reviewed, and that still has no satisfying conventional explanation. We are going to look at that evidence carefully, without prejudice in either direction. Not dismissing what is extraordinary, but not accepting it without scrutiny either. The truth, as always, is in the details. The Inca Empire covered over 3,000 kilometers of the Andes mountain range, from present-day Colombia to northern Chile, through terrain so rugged that even today some areas are accessible only by mule or on foot. The Inca administered this enormous empire with extraordinary efficiency, running a road system longer than Rome's, maintaining storehouses of food and weapons throughout the mountains, and deploying armies of hundreds of thousands. They did all of this without the wheel, without horses, until the Spanish arrived, and without a riding system in the conventional sense. And they did it connected by bridges made of grass. Not any grass, and not any bridges, but woven grass suspension bridges across mountain gorges of up to 60 meters, capable of supporting the weight of llama trains, and according to Spanish chroniclers, of 10,000 soldiers crossing simultaneously. Modern materials scientists have spent decades analyzing how these bridges were made, and they have found that the fiber used a high-altitude Andean grass called ichu, when twisted and braided using specific Inca techniques, achieves a tensile strength approaching that of modern steel cable relative to its weight. The most famous surviving Inca rope bridge is the Huehuechaca Bridge across the Apurimac River in the Cusco region of Peru, which is still rebuilt every June in a 4-day community ceremony using exactly the same techniques used by the Inca 500 years ago. The community of Huancaire takes responsibility for the bridge and uses ichu grass collected from the surrounding highlands to weave the cables. Each bridge requires approximately 20 kilometers of hand-twisted grass rope, and then assemble them into the suspension structure. But Huehuechaca is a modest example. The Spanish colonial chronicles describe Inca bridges hundreds of meters long, spanning gorges 100 meters above raging mountain rivers. Some of these bridges were so important to the empire's logistics that dedicated keepers maintained them year-round and were exempted from all other labor taxes. The engineering principles behind the Inca rope bridges were not understood by European visitors for centuries. The Spanish, who had nothing comparable in their own engineering tradition, initially refused to cross them. When engineers finally analyzed them in the 20th century, they discovered that the Inca had independently developed many of the same mathematical and structural principles that underlie modern suspension bridge engineering, including the use of curved cables under tension to distribute loads, the value of a flexible deck that moves with rather than against dynamic loads, and the importance of maintenance protocols for a structure that degrades and must be regularly replaced. In 2019, MIT engineers built a physical model of a larger Inca bridge and found that it was not merely strong enough. It was catastrophically over-engineered for its actual load requirements, suggesting the Inca had a safety margin built into their design that goes far beyond empirical necessity. How did they calculate that? What did they know about bridge engineering that we are still trying to reconstruct? This is where our investigation begins. Stay with us, because the further we go into the evidence, the more extraordinary it becomes. The story you think you know is only the surface. Beneath it lies something far more remarkable. Let us begin. Before we go further, if you are finding this investigation compelling, please take a moment right now to like this video, drop a comment below with your thoughts, and share it with someone who loves a good historical mystery. If you are watching on YouTube, hit subscribe and tap the bell icon so you never miss a new episode. If you found us through Facebook, tap follow on our page. It takes just a few seconds, and it genuinely helps us keep making these documentaries. Now, let us get back to the investigation. Before we examine the specific evidence, we need to step back and understand the context. This case does not exist in isolation. It sits within the wider world of ancient technological anomalies, and to properly evaluate what we are looking at, we need to understand the broader picture that surrounds it. The official story of technological progress follows a reassuring arc. Stone tools giving way to bronze, bronze to iron, iron to steel, and finally, the Industrial Revolution catapulting humanity into the modern age. In this narrative, each generation inherits a slightly more sophisticated toolkit than the last, and no knowledge is ever truly lost. It is a comfortable story. It is also, in key respects, demonstrably false. History is littered with technological achievements that appeared centuries before their supposed invention, vanished after the cultures that created them collapsed, and were reinvented, often with great difficulty, by later civilizations who had no idea the knowledge had ever existed. Roman concrete was stronger and more durable than most modern concrete and was not matched again until the 21st century. Greek fire, the incendiary weapon that protected the Byzantine Empire for centuries, has never been fully reproduced. Damascus steel, capable of holding an edge that modern metallurgists struggle to replicate, disappeared with the craftsmen who made it. These are not myths. They are documented historical losses of genuine technical knowledge. When we encounter an object from the ancient world that should not exist, a battery from Baghdad dated to the Parthian era, a computing mechanism salvaged from an ancient shipwreck, a map showing geographical features that were not officially discovered for another millennium, the temptation is to dismiss it as misidentified or misstated. That dismissal is sometimes warranted. But when such objects accumulate, when the pattern becomes too consistent to ignore, the honest response is to ask whether our model of ancient capability is simply wrong. This context matters because it tells us something important. What we are about to investigate is not an isolated curiosity. It is part of a pattern that researchers in multiple fields have been independently documenting for decades. And patterns in science demand explanation. With that foundation in place, let us now turn to the specific case at hand. Now we reach the heart of the matter. The core evidence surrounding the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it, is more extensive, more verified, and more troubling for conventional explanations than most people realize. Let us walk through it systematically, fact by fact, and allow the evidence to speak for itself. We are not going to speculate here. Every point that follows is documented in peer-reviewed publications, official archaeological records, or government archives that are publicly accessible. The question is not whether these facts are real. The question is what they mean. Consider this first extraordinary detail. The Quesuachaca Bridge across the Apurimac River is the last surviving Inca-style rope bridge still maintained using traditional techniques. It spans approximately 36 meters across the river at a height of approximately 9 meters above the water, and is rebuilt entirely from scratch each June by the 4 communities of Huancaire, Chorpabanda, Chiquehua, and Sikalana, Quehu over 4 days. The entire approximately 36-meter bridge requires roughly 20 kilometers of twisted ichu grass rope, which is prepared by hundreds of community members in the weeks before the rebuilding ceremony. Quesuachaca was inscribed on UNESCO representative list of the intangible cultural heritage of humanity in 2013. This single data point, if taken in isolation, might be set aside. Anomalies happen. Instruments malfunction. Researchers make mistakes. But as we continue, you will see that this is not an isolated anomaly. It is part of a consistent and documented pattern. But that is only the beginning. Researchers also discovered Inca Rope Bridges used 6 primary cables, 2 for the deck surface, 2 for handrails, and 2 additional load-bearing cables, woven from ichu grass, Stipa ichu, a coarse, high-altitude Andean grass that grows above 500 meters elevation. The grass is harvested, dried, and then hand-twisted into progressively larger ropes through a process called knotted loop braiding, working up from individual grass strands to finger-width cords, to arm-thick cables, to the massive suspension cables of the final bridge. The tensile strength achieved by this multi-stage twisting process has been measured by modern materials scientists at approximately 14 megapascals, comparable to high-grade rope made from natural fibers and within an order of magnitude of low-grade steel cable. Now, a skeptic might propose an alternative explanation for this, and that is entirely reasonable. We should always test alternative explanations before accepting extraordinary ones. The problem is that the alternative explanations, when examined carefully, create more problems than they solve. The mystery deepens when we examine. Spanish colonial sources describe Inca bridges of enormous scale, far exceeding Quetzalcoatl. Cieza de León, writing in the 1550s, describes a bridge across the Desaguadero River, linking Lake Titicaca to the Pacific drainage, made entirely of tadora reeds woven into a floating platform structure 900 feet long, approximately 275 meters. Pedro de Cieza de León also describes the Great Bridge at Huánuco Pampa, which could support cavalry and artillery, meaning the Spanish actually used Inca bridges for military logistics in the decades after the conquest. The bridge at Pongo de Maynique on the upper Urubamba was reportedly 150 meters long and served as a key link in the Inca road system connecting Cusco to the Amazon lowlands. This is where the conventional account begins to strain. Each individual fact might be dismissed or minimized in isolation, but the cumulative weight of the evidence is another matter entirely. Perhaps most remarkable of all, the Inca road system, Quhapacnian, of which the rope bridges were a critical component, connected the empire across approximately 40,000 kilometers of paved road, a network longer than the Roman road system at its peak. Unlike Roman roads, which were built to accommodate wheeled vehicles and were accordingly wide and rigidly constructed, Inca roads were narrow, 1-4 meters wide, designed for foot traffic and llama caravans, and incorporated flexible elements including rope bridges, drainage systems, and switchback ramps that adapted to the extreme topography of the Andes. The Quhapacnian was designated a UNESCO World Heritage Site in 2014, with segments across 6 Andean countries. Researchers who have examined this evidence have described it as genuinely difficult to explain within the accepted framework. These are not fringe commentators. They are credentialed academics publishing in mainstream journals, raising questions that the field has not yet satisfactorily answered. Then there is the matter of the Inca had dedicated bridge keepers called Chacasuyu who were responsible for maintaining specific bridges on the road network as their contribution to the Mita system of labor tax. Bridge keepers were exempt from other forms of labor taxation, and their communities were responsible for supplying the materials needed to maintain the bridges in their care. This institutionalized maintenance system meant that every bridge on the Inca road network was under regular surveillance and repair, and colonial records indicate that major bridges were completely rebuilt on a regular cycle, some as frequently as every 2 years, because natural fiber bridges degrade and must be renewed. The Quetzalcoatl annual rebuilding ceremony is a direct continuation of this pre-Columbian maintenance tradition. What makes this particularly significant is its independence from the previous points. This is not a case of one theory requiring another. These are separate lines of evidence converging on the same uncomfortable conclusion. Adding to the enigma is this finding. A 2019 study by MIT engineers Carly McNally and John Ochsendorf used historical records, physical modeling, and materials testing to reconstruct the engineering principles of larger Inca suspension bridges. Their analysis found that the Inca bridges incorporated a passive damping mechanism. The natural elasticity of the twisted ichu grass combined with the catenary shape of the suspension cables that made them remarkably resistant to wind-induced oscillation. This is precisely the engineering challenge that caused the 1940 collapse of the Tacoma Narrows Bridge in Washington state: aerodynamic resonance between wind and bridge structure. The Inca had apparently solved this problem empirically 5 centuries before Western engineers encountered it theoretically, by using flexible materials and specific cable geometries that dissipate rather than amplify oscillating loads. Taken together, these facts form a pattern that cannot be explained by coincidence. See misidentification or methodological error. Each piece of evidence has been examined by skeptics. Each has been subjected to alternative explanations, and in each case, the alternative explanation falls short of accounting for everything that has been documented. We are left with a body of evidence that demands explanation and an accepted narrative that does not provide one. This is where serious inquiry begins. Now that we have established the evidence, we need to examine the theories that researchers have proposed to explain the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it. This is where the debate becomes most intense, because the theories reflect not just different interpretations of the same evidence, but fundamentally different assumptions about what is possible and what the past looked like. Understanding these theories is not just an academic exercise. Each one has been championed by serious researchers with genuine credentials, and each one captures something that the others miss. The truth, if it is ever established, will likely draw on elements of several. The first major explanation proposed by researchers holds that the empirical engineering theory, supported by most scholars, holds that Inca Rope Bridge technology evolved over many centuries through systematic trial and error, with each generation of bridge builders learning from the failures of previous designs and accumulating practical knowledge about load limits, material behavior, and structural stability. Under this view, the Inca engineers achieved sophisticated results not through theoretical understanding, but through multi-generational empirical learning encoded in the building traditions of the Chacasuyu communities. The knowledge was transmitted not in writing, but through practice, masters teaching apprentices in an unbroken chain from before the Inca Empire to the present Quechua community. This interpretation has significant academic support and is backed by substantial evidence, but it is not without problems. Critics point out that it requires assumptions that go beyond what the evidence strictly supports, and that key predictions of this theory have not been confirmed by subsequent research. It remains contested, and the contest is productive. A rival school of thought argues that the Quipu engineering theory proposes that Inca engineering knowledge was encoded in quipus, the knotted string recording devices that the Inca used as their primary information storage system, while quipus are traditionally interpreted as numerical recording devices. For taxation, census, and inventory data, a significant minority of researchers, including Gary Urton, have proposed that some quipus encode narrative or technical information. Under this theory, bridge building specifications, cable diameters, knot types, span calculations may have been preserved in quipu form and transmitted across generations as technical manuals. If true, the quipu system may represent a form of engineering documentation functionally equivalent to written technical literature. This theory is controversial, and deliberately so. Its proponents argue that the evidence demands an explanation outside the conventional framework. Critics counter that extraordinary claims require extraordinary evidence, and that the evidence presented, while suggestive, does not yet meet that standard. The debate continues in peer-reviewed literature. Perhaps the most unconventional theory suggests that the Andean cosmological engineering theory, developed by anthropologist Gary Urton and art historian Sabine Hyland, proposes that Inca engineering was inseparable from Inca cosmology, that the design of bridges, roads, and other infrastructure was governed by ritual and calendrical considerations alongside practical ones. The annual rebuilding of Queswachaka is timed to coincide with the dry season and with specific community ritual calendars, suggesting that maintenance was integrated into ceremonial life. Under this model, Inca engineering knowledge was transmitted through ritual practice as much as through technical apprenticeship, making the engineering and religious traditions effectively identical. What is striking about this debate is not merely that experts disagree. That is normal and healthy in science. What is striking is the quality of the disagreement. Serious researchers, working from the same body of evidence, reaching genuinely different conclusions. That level of fundamental disagreement, when it persists over decades, is a signal that something important has not yet been understood. The question is not which of these theories is right. The question is whether any of them is right, or whether the truth is something that none of the current frameworks has yet been able to capture. The case surrounding the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it, does not rest on speculation alone. What distinguishes this investigation from pure mythology is the existence of documented, physical, verifiable evidence, material that has been examined by credentialed researchers and whose authenticity is not seriously disputed. What is disputed is its interpretation. Let us review the most significant documented evidence as objectively as possible. We are not going to cherry-pick the data that supports a preferred conclusion. We are going to lay out what exists and let you draw your own assessment. Physical evidence supporting this account includes the Queswachaka Bridge itself is the most important evidence for Inca Rope Bridge technology. The bridge's measured performance characteristics, its load capacity, several tons across a 36-meter span, its resistance to wind loading, its maintained safety under the dynamic loads of multiple people crossing simultaneously, provide a physical baseline for understanding what the technology can achieve. When MIT engineers modeled the Queswachaka cables in 2019, they found that their measured tensile strength significantly exceeded what was required for the bridge's actual load conditions, confirming a built-in safety factor that argues for sophisticated engineering understanding rather than mere practical adequacy. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. Investigators have documented. Historical documentation from Spanish colonial sources provides evidence for the scope and capability of the larger Inca bridges. The accounts of Cieza de León, Garcilaso de la Vega, the Inca Spanish scholar, and several other 16th-century chroniclers are consistent in describing bridges capable of supporting cavalry, artillery, and large military formations. These accounts were written by people who had used the bridges themselves and had every reason to describe them accurately. They needed to know whether the bridges would support their equipment. The consistent Spanish descriptions of functional, large-capacity bridges across major Andean gorges provide strong evidence that the Inca regularly achieved structural feats beyond what Queswachaka demonstrates. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. On-site analysis revealed. Materials analysis of ichu grass rope conducted by MIT in partnership with Peruvian archaeologists has produced quantitative data on the tensile properties achievable through Inca braiding techniques. The key finding is that the multi-stage twisting process, individual strands to cords to cables, produces a composite material with higher tensile strength per unit mass than the raw grass itself, because the twisted structure distributes stress across individual fibers and prevents propagating fractures. This is the same principle underlying modern composite materials and modern rope construction. The Inca achieved it with grass and hands, without any theoretical framework for composite materials science, through empirical techniques refined over an unknown number of generations. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. Each individual piece of evidence might, in principle, be explained away. A single anomalous artifact might be misidentified. A single anomalous date might reflect contamination. A single anomalous eyewitness account might reflect misperception. The question is whether all of the evidence can be explained away, and whether the explanations required are more or less plausible than the evidence itself. When multiple independent lines of inquiry converge on the same conclusion, that convergence is the most powerful signal in empirical science. And that is exactly what we are seeing here. We have examined the history, the evidence, and the theories surrounding the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it. Now, we need to ask the question that is sometimes overlooked in discussions of ancient mysteries. Why does this matter? What does it mean for us today? It would be easy to file this away as an interesting historical curiosity, a puzzle from a distant past with no bearing on our present lives. That would be a fundamental mistake. The questions raised by this case touch on issues that are directly relevant to who we are, where we came from, and what the human story actually looks like before the period covered by conventional history. The Queswachaka Bridge community continues to rebuild their bridge each June in what has become both a living cultural tradition and one of Peru's most significant intangible heritage assets. The UNESCO inscription in 2013 has brought international attention and some funding to the community, and the annual rebuilding ceremony attracts researchers, documentary filmmakers, and tourists alongside the community members who are the primary participants. The four families who hold the hereditary responsibility for the bridge, including the Chakasuyu knowledge that has been transmitted continuously from the Inca period, have become internationally recognized as living repositories of an engineering tradition that is otherwise extinct. Research on Inca Rope Bridge technology has accelerated in recent years, driven by a combination of materials science interest, heritage preservation concern, and the recognition that Andean engineering traditions contain practical knowledge with modern applications. The passive damping properties of ichu grass rope bridges have attracted attention from civil engineers studying earthquake-resistant construction, and the community-based maintenance model of the Queswachaka tradition has been studied by development economists as a model for sustainable infrastructure in remote mountain communities. MIT's ongoing work with the bridge community represents a rare example of engineering researchers learning from an ancient tradition rather than the reverse, acknowledging that the Inca solved structural engineering problems that Western engineers did not formalize until the 20th century, and doing so with nothing but grass, hands, and 5 centuries of accumulated knowledge. Furthermore, the tools available to investigate these questions are advancing rapidly. Satellite imaging, ground-penetrating radar, ancient DNA analysis, isotopic tracing, and deep-sea sonar are all providing capabilities that previous generations of researchers could only dream of. Cases that were genuinely unresolvable 10 years ago are now open to new analysis, and the findings, consistently, are expanding rather than contracting the mystery. The investigation continues. New discoveries are being made. New analyses are being published. New voices are entering the conversation from disciplines that were not previously part of the discussion. The answers, when they come, and they will come, will not merely solve a historical puzzle. They will force a fundamental revision of assumptions that underpin our entire understanding of human history and human potential. We have now walked through the complete case of the Inca Rope Bridges, a fiber technology so advanced that modern engineers are still reverse engineering it, from historical record through the physical evidence, across the competing theories, and into the modern significance of what remains unresolved. What the story of Inca ultimately reveals is not just a historical puzzle. It is a mirror. It reflects our assumptions back at us, our assumptions about what ancient people were capable of, about how knowledge is gained and lost across the centuries, and about the relationship between what we know and what we merely think we know. The evidence present in this documentary is real. The questions it raises are genuine. The debate among researchers is ongoing, and that is healthy. Science is not a set of conclusions. It is a process, and the process requires that we remain open to evidence that challenges what we thought we knew, however uncomfortable that challenge might be. If you came to this documentary as a skeptic, we hope the evidence gave you something to think about. If you came as a true believer, we hope the critical examination gave you a more nuanced picture. The truth, as always, lies in the evidence, not in what we want to be true. Thank you for watching. If this investigation sparked your curiosity, please help us reach more people. If you are watching on YouTube, subscribe to the channel and hit the notification bell so you never miss a new documentary. If you are watching on Facebook, tap the follow button on our page to stay connected. We publish new documentaries every week, covering the full range of historical mysteries that the mainstream has not yet adequately explained. Leave a comment telling us which case you want us to investigate next. The conversation continues. The investigation never ends.